the last lecture, we reached a milestone in the course. We completed discussion on two-dimensional point groups and plane groups. In this lecture, we will start discussion on extension to the third dimension. So, we are going to extend whatever we have done to 3 dimensions. And in this, basically the two-dimensional point groups will become 3-dimensional point groups and the plane groups will become what we call as space group. So, first we will consider the 3D point groups. One thing that one can note is that all the two-dimensional point groups we had discussed would simply become or can straight away be extended to 3-dimensional point groups, which means that we had 10 two-dimensional point groups. Therefore, we immediately have 10 3-dimensional point groups, and this could be looked at it this way. For example, if you consider the 2D point group two mm. Now, this 2 mm point group, there are 2 mirrors and at the intersection of the 2 orthogonal mirrors, we have 2-fold rotation axis, and that is how this terminology of 2 mm comes. Now, imagine that there is a third axis perpendicular to this particular point group, and this point group then can be imagined in 3 dimensions as follows, that I have now 2-dimensional rotational axis and there are 2 mirrors which now have become planes in 3 dimensions. So, this is one of the mirrors and a second mirror one can imagine perpendicular to the first mirror. Something like this. So, I have basically I can say that perhaps this is M1 and this is M2 and my rotational axis is along the line of intersection of the 2 mirrors. So, this is simply an extension of the 2-dimensional 2 mm group to the third dimension. Now, but so we get these 10 3-dimensional point groups simply an extension of the 2-dimensional point groups. But now, in 3 dimensions there is something else that we need to look at first. In 2 dimensions, we cannot have rotation axes intersecting each other, but once we go into the 3 dimensions, now the intersection of rotational axis becomes possible. So, for instance, I have a rotation axis, let me call this as axis A, and let us say there is a rotation of alpha around this rotational axis, and there is another rotational axis which is at some angle to this, and one can call this again as B beta, where beta is the amount of rotation one can give around the second rotational axis. So, let us take this thing. What would happen? What would be the result of a rotation of alpha around A axis followed by rotation of beta about the B axis? What kind of a symmetry operation we can have? So, let us take asymmetric motif, and let us say this is my asymmetric motif. I give a rotation of alpha, as a result my asymmetric motif rotates by alpha and possibly comes at this location. So, this is my first motif, it goes to motif number 2. Now imagine that one gives rotation of beta about the b axis. Now where does this motif 2 go from there? So let us say that this is my rotation of beta and the motif moves to this location 3. So I have 1 going to 2 by A alpha, 2 going to 3 by B beta. Now the third symmetry operation which can take from 1 to 3, this is what we have to figure out. Now since both of them are rotation operations around A and B, therefore there is no change in handedness, so there can be no inversion or reflection possible, and the only other operation that can take place is a third rotation axis. So we can imagine that one has a third rotation axis which is axis C, which will take from motif number 1 to motif number 3, and that rotation axis has some angle gamma. So therefore I can say that going from 1 to 3, or the result of operation of A alpha followed by B beta, is the operation of C gamma. Now if in 3 dimensions, if you look at this, these rotation axes will be at some angular position with each other. So let me put some angles to this. Let us say rotation axis C and B, the angle is A. Between A and C, let us call that angle as B, and then finally between the angle between axes A and B is the angle C. So really I have actually now a bunch of angles here. I have alpha, beta, gamma are the rotations about the axes A, B and C, and then I have the angles a, small b and small c, which are the angles between the rotation axes themselves. And what we want to do is we want to find some kind of a relationship between these angles. And through that relationship we can determine what are the possible combinations between, I should say, crystallographic rotation axes, which means that these 3 rotation axes A, B and C can be basically the 5 crystallographic rotation axes that we have. So essentially what we want to do now is to figure out how to combine rotation axes in 3D. So before I go to a general solution, let me take an specific example . Specific example using matrices. So let us recall our rotation matrices. For example, let us consider Cartesian coordinates x, y and z, and then if you go back to one of the earlier lectures, rotation about x through some angle, and I will call that rotation matrix corresponding to this rotation, and let us say this is some rotation theta. So R x theta, the matrix that I have is 1 0 0 0 cos theta minus sin theta, then I have 0 sine theta cos theta. This is a rotation axis corresponding to a rotation of angle theta about the x axis. Similarly, one can write about the y axis r y theta, and that is cos theta 0 sine theta, then I have 0 1 0, I have here minus sine theta 0 cos theta, and then finally about the z axis one has cos theta minus sine theta 0, then I have sine theta cos theta 0 0 0 1. So, these are the three matrices that I have rotations about the axes x, y and z that we had done in an earlier lecture. You can go back to the earlier lecture and see how we got these matrices. Now, imagine that about the x axis I have a twofold rotation axis, about the y axis I have a twofold rotation axis, which means that about both of these axes theta is equal to pi. So, I am giving a 180-degree rotation about x, I am giving a 180-degree rotation about y. So, essentially the operation that I am looking at is r x theta followed by r y theta, and I want to find out what is the resulting rotation operation that would be there. This combination then clearly one can express it now and in the form of matrix multiplication. So, about the y axis first I am going to write down theta is pi. So, cos theta becomes minus 1 0 0, I am looking at this particular matrix. The next row is 0 1 0 and the third row is 0 0 minus 1, theta being pi, and then I multiply this matrix into the rotation about x, which would be 1 0 0 0. Now, I am looking at this particular matrix, cos theta minus 1, cos pi is minus 1 0, and I have 0 0 minus 1. The resulting multiplication row into column. So, the first row will become of the result would be minus 1 0 0, second will be second row here into the individual columns, and I am going to get 0 minus 1 0, and then finally I am going to get 0 0 1. So, this is a resulting matrix. Now, what does this particular matrix correspond to? And very clearly the result is, if you look at the rotation matrix about the z axis, and you will see that when you put theta is equal to pi, you are going to get exactly this matrix, which means that this is simply equal to r z pi. Now, what does this mean? What basically this means is that if I have twofold rotation axes perpendicular to each other, and if I perform the 180-degree rotation about these axes, the resulting rotation would be about a third axis perpendicular to the two axes x and y, which is the z axis, which basically means that when I combine twofold rotation axes, I can combine it in only one way, and which is that all the three axes should be perpendicular to each other. So, in fact, what we have done here is we have come up with actually a point group 2 2 2. So, this is a point group in 3 dimensions, and the three twofold rotation axes will be perpendicular to each other. So, essentially in a very specific case, when alpha equal to 180 degrees, beta 180 degrees, gamma 180 degrees, A, B and C, all of them have to be 90 degrees. This way one can actually find all possible combinations using matrices, but it is much simpler to look at this problem because we want to find a general solution, so that we can easily find out what are the various combinations that are possible. In order to do that, we will actually take recourse of geometry rather than matrix multiplication. So, from geometry, we want to find a general solution for the relationship between alpha, beta, gamma on one hand and A, B and C, which means that if I combine 3 arbitrary rotation axes, what should be the angles between the axes A, B and C. Now, in order to do this, what we are going to do is we are going to imagine that the 3 axes A alpha, B beta, C gamma intersect at a point which is the center of a sphere of unit radius. So, you can imagine a thing that I have a sphere and through this center I have rotation axis A, another rotation axis coming out from the center is the rotation axis B and a third rotation axis C. So, this is rotation alpha about A, about beta about B and gamma about C. Now, these 3 axes coming out from the center of the sphere will intersect at a point on the surface of the sphere, and that point we will simply call them as A, B and C. And the points of the rotation axis with the surface of the sphere is called, these points are called as pole. So, each of them I have pole A, pole B and pole C. Before we get into this discussion, I need to take a little bit of digression into some properties of spherical geometry. So, let us do a digression. Imagine now there is a sphere and there is a circle drawn on the surface of the sphere such that this is a circle of the largest possible radius that I can draw on the surface of the sphere. And what is the largest possible radius of the circle of a sphere is only if the circle on the surface of the sphere, its center coincides with the center of the sphere. For example, one can think of a sphere and one can think of the equatorial plane. So, that would be a circle of largest sphere, largest radius, or basically same radius as the sphere itself. Now, such circles, and there will be innumerable number of circles, these are called as great circles. So, if there is a point P and there is a point Q, what is the, just like in the Euclidean plane, when we talk about 2 points, what is the shortest distance between 2 points? We say the shortest distance is a straight line. On the surface of the sphere, the shortest distance between P and Q, but after all I can draw all kinds of lines through P and Q, all kinds of arcs through P and Q. The shortest distance between P and Q would be the arc which is part of the great circle. So, P and Q, the shortest distance, is given basically by the arc of the great circle as shown in this figure. And this distance, if we imagine that I have a sphere of unit radius, then one can see that the distance would be the angle subtended by P and Q to the center, and that angle subtended, let us say, is alpha. So, this distance then, so PQ is equal to alpha. Now, let us take a perpendicular to the plane of the P circle from the center of the sphere. That perpendicular could be something like this, and let us say or that this perpendicular is denoted by A, or rather AO, you can imagine, O being the center of the sphere. So, now if AO was a rotation axis, and if I rotated the point P by an angle of alpha, then point P will move to the position Q. Now, keep this in mind. Now, let us consider, and of course, this perpendicular OA would intersect the surface of the sphere at some point A. So, this is which basically nothing but the pole. So, we say that for the arc PQ or the great circle that is drawn here, its pole is the point A where the perpendicular intersects the surface of the sphere. Now, consider 3 poles consider 3 poles A, B and C. On the surface of a sphere of unit radius. Let me call this as C. And the center of the sphere is designated as O. So, I have poles A, B, C, which are the poles of the axes OA, OB and OC. These could well be considered as rotation axes, as we will see later. Now, again we invoke this definition that what is the shortest distance, let us say, between A and B will be the great circle that goes through A and B, and there will be a unique great circle that will pass through any 2 points on the surface of the sphere. So, that, and I will draw only part of the arc of the great circle. So, AB is joined by an arc of the great circle, which is the shortest distance between A and B. Similarly, A and C will be another great circle, and between B and C there will be a third great circle. The distances between B and C, the distance I can let me designate it as A. The distance between A and C, the poles A and C is designated as B, and the distance between A and B is designated as C. And remember that this is, the sphere has unit radius, that is why I can talk in terms of distances. Then I have 3 more angles in this. So, there is an angle here which is the interior angle. So, this is like a spherical triangle. Okay. This is the equivalent of the Euclidean triangle. We have a triangle on the surface of a sphere. So, this is angle at vertex A, angle at vertex B, and there is an angle at vertex C. So, if you look at it, essentially there are 6 angles that we have. We have the angles ABC, and we have the angles at the vertices, and let us call those angles as capital A, capital B, capital C, denoted by the vertex term itself, which means let me call this as A, B and C. Now, there is a relationship between these sets of angles, capital A, capital B, capital C and small a, small b, small c. And that relationship, just like we have properties of a triangle in the Euclidean plane, we also have properties for a spherical triangle as well. And that is where I bring in the cosine rule. Now, this cosine rule can be written in many different formats. I am going to write in one particular format which is useful to us. So, cosine of A equals cos A plus cos B cos C, all the angles at the vertices, divided by sin B sin C. Similarly, cosine of B, small b, can be written as, and you can see the symmetry of the equation, and just by inspection one can write that cosine of small b is cosine B plus cos C cos A divided by sin C sin A. And the third equation, the cosine of small angle C is cosine C plus cosine A cosine B divided by sin A sin B. We will keep this in mind, this set of equations under the cosine rule. And now, considering the three rotation axes intersecting at the center of the sphere and how we solve the general problem to look at how do I get the relationship between alpha, beta, gamma and the angular positions of the axes A, B and C. Thank you.